Okay, we are all set and running. Okay, so I have a couple of questions for you then. Uh, okay, so what makes the world go round? We don't know, but today I'm going to tell you something that makes programs go round, uh, and that's called recursion. All right. Sorry, it's a poor joke, but yes, I don't know what makes the world go round, but I know what makes programs go round, and that's called recursion. And since we won't have loops in our language letters, we are going to use recursion. Next best thing, right? And since we are doing functional programming in this class, we have temporarily banned loops anyway, so might as well get started with recursion. And so we are looking at recursion in lattice. We already looked at recursion in Scala. We looked at those concepts up front. Today we are just going to look at recursion in lattice, the language lattice. All right. So with that being said, let's get started and see where we go. All right. Okay. So last lecture, we started looking at recursion, and we saw that we would allow you to write functions like this. Uh, and this is our favorite recursive function, the factorial function, else x times factorial x minus 1. I mean, we are bored of the factorial function, but you know, it's everyone's favorite recursive functions. I mean, given all the political posturing that's going on, I'm tempted to say it's America's favorite recursive function. All right, but here you go. This is factorial. And we wrote this function last time. We also saw last time that if you didn't have this keyword that indicates that it's a recursive definition, then this is wrong. Oh yeah, it's the freedom function, right? Yes, I like it. Yeah, so if you don't have this, right? If you don't have this, if you don't have the recursive keyword, last lecture we saw that this breaks. And this breaks because this fact is nominally out of scope without the recursive keyword. But we added an extra keyword called rec to our language. And now we, by fiat, we say this factorial, this fact is in scope on the right-hand side. Okay, number one. And number two, we saw that we could only do this for things like functions. If you did this for things that were in functions, like if you did something like let rec x equals x plus 1 in x times x, then this is undefined, bad, horrible, whatever you want to call it. This makes no sense at all because you can't give x any value that's going to satisfy x equals x plus 1. All right, so we are going to have to deal with nonsense like this. And this is the rule number one of programming language design. When you design a programming language, you do not design for reasonable users of the programming language. You have to design for all possible programs that could ever be written should be handled. Okay, and that's a huge thing. All right, so now what we need to do is we need to today sort out how are we going to do this let rec in our language. All right, so we are going to allow let rec, but we are only going to allow it in the context of a function definition. So the rule in lettuce now, so the rule in lettuce, and we are going to enforce this, is whenever you have a let rec and you define something, let's call it blah, it better be a function that you are defining. So it better be a function in water. Okay, so this is going to be the template. So this is going to be the body of the function. You're going to have a formal parameter, but I'm going to force you to do this. I am going to force you never to do something like what I have written in red. And that's important. Okay, so today we need to say that. And how do I force you? The easiest way to force you is to define my abstract syntax. So I'm going to define my abstract syntax in a way that can only accommodate expressions of this form, where you're using let rec to define a function. That's the only form I'm going to accommodate. If you try to write a program like this, so if you try let rec x equals x in x, my parser is going to try and parse this, and it's going to come up with a syntax error. Okay, I'm going to deal with it in my parser somehow. Okay, and since parsing is a bit beyond the scope of this class, I'm not going to talk about how do I write my parser to deal with it. But let's just assume that programs like this are rejected summarily as being bad syntax, and we go from there. All right, so the only syntax that's allowed is when let rec defines a function. Okay, now, so then how do we deal with this in the abstract syntax world? Well, in the abstract syntax world, we are going to write our grammar for expressions. We are going to have our usual suspects. Our usual suspects, we are going to have a constant. We always have to have a constant. Okay, that joke didn't go over well. All right, fine. We need to have an identifier and so on. So all the usual suspects. All right, so we need to have all the usual suspects, including our plus, our minus, and all of that. Okay, so we need that. What else do we need? We can have our let bindings. We can have our function definition, the non-recursive style function definition. So that would be, you give me a string, you give me an expression. That's from last lecture. We can also have function calls, expression. Okay, so this is from last lecture. And now comes the main thing that we are going to define today is the let rec. So I am going to have a mix up of two things. I'm going to have a mix up of a let binding. So I'm going to have a mix up of a let binding plus a function definition. And official, I guess the term for it is portmanteau. It's basically like a pastiche. Okay, I'm going French today. All right, so it's like a combination of the two. So you have to have a combination of the two in your abstract syntax. So what does the combination look like in my abstract syntax? So a let rec is going to have a lot of things in it. So it's going to have a string, okay, and this is going to be like this. So let me write a concrete definition and then write abstract definition. So it's going to be let rec some name of the function equals function of a parameter of the body of the function in some expression. Okay, so this is the template that I need to cut. So I need to know the name of the function. So that's going to be the first string argument. I need to know the formal parameter here. That's going to be my second argument. I need to know the body, and that's going to be my third argument. And I need to know the thing that comes after the in, that's going to be my fourth argument. So when I say let rec string expression, it's basically a template that's being filled up like this. This first string is the name of the function. This second string is the name of the formal parameter. The third argument is an expression. This is the body of the function. And the fourth argument is expression. It's the part after the in. And this is going to be a two-in-one thing. So it's going to be a two-in-one thing in the sense it's going to have both a let binding and a function call mixed up. And this way, I make sure you will never be able to write a let binding, a let rec binding like this. This kind of a binding does not even have a place in our abstract syntax. We don't even have that concept. Questions so far? Okay. Hopefully this is good. Hopefully this is good. So in that case, how does our factorial function look then? So how does our factorial function look? In concrete syntax, it looks like this. Let rec fact equals function of x. Okay. And then there's going to be the body. If x less than equal to 1, then 1, else x times fact of x minus 1. Okay. In. And then you have fact of 10. So as a let in the abstract syntax, Okay, so this is going to look like this. In the abstract syntax, is everyone still okay, hearing me? Did I lose people? Okay, great. So in the abstract syntax, this is going to look like this, right? So it's going to look like a let rec, and then the name of the function, fact, the name of the formal argument, x, the body, which is the AST definition of this guy, body, which is going to be an if then else. This is going to be complicated to write, so I'm not going to write it fully. If then else, LEQ, ident of x, blah, 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 blah. So this entire thing is going to be the body in abstract syntax, all right? And then comes the part after the in, which is this part. And this is going to be a fun call. We are still going to use the old mechanism because once a recursive function is defined, it's still a function. So we don't care what kind of function it is when you call a function. So it's going to be func call ident of fact const of 10. So this whole mess is going to represent our factorial definition with the let rec and the part where the definition gets used with the in. Everyone with me so far? This is not, pretty, but it works, right? It works. Is that okay? Okay, can I go over the names of the 4 parameters of the let rec? Absolutely. So the first parameter is the name of the function. So like fact, the name of the function, of the function you are defining. The second parameter is the formal name of the formal parameter, name of the formal parameter. The third parameter is the body of the function body, which is this whole mess, if then else, that defines factorial. And the fourth parameter is everything afterwards, because I'm doing like let blah, 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 in blah, blah, blah. The thing that comes after in is the fourth parameter, and that's an expression. So that's the fourth parameter. Is that okay? All right, very good. So with all of this in place, I now need to worry about let bindings. And I still haven't solved the following issue. The big issue here is, remember, this name, fact, name of the function, likely also occurs in the right-hand side. So you have a fact somewhere in the body. So inside the body, you have that recursive call to fact. Okay, so then the question is, how do I deal with it? Is that okay? Okay, now I'm going to talk about how do I deal with it. And the answer today is I'm going to talk about how to deal with it using something called circular scopes or circular environments, as opposed to the more elegant method, but the more complicated method, which is the method of Y combinators. Okay, so now since you're in class, I'm going to let you in on a small secret. Okay, well, I'm not going to keep it a secret, but I'm going to let you in on something. And the something is this. So if you go to, let's see, how do I get to my browser? Just a second. Okay, it looks like, yeah, hold on. Let me share my browser. Give me a second. Okay, so if you go to the notebook, I have written up all of this in a notebook called Recursion in Lattice, all right? And everything is there, including the whole Y Combinator mess. So what you need to make sure is the Y Combinator part, okay? So the Y Combinator part, so I have defined all this let rec business. I have shown you exactly all of these things, okay? This handling recursion using Y Combinator is not in syllabus. So you really do not need to worry too much about this whole exposition on how to write a recursive function as a non-recursive function using the Y Combinator trick. Okay, I'm not going to worry about having you do that, though I have given you the full code for it. Okay, and this is the recipe for converting a recursive definition into a non-recursive one. And you know, I do that implicitly. I'm not going to go over this. I kind of went over this in like 15 minutes last lecture, where we saw that you know, breaking that circular chain and cascading from one definition to what is next, and then trying to introduce the circularity very carefully. We saw all of that last time. I'm not going to reiterate that. That part is not in syllabus. The part that I'm going to work on is this part, where I'm going to show you how a circular environment solves the problem completely. Okay, so today I'm going to just go over the circular environment, and that is all I would expect you to know. I will not expect you to know the Y Combinator business. That's interesting, and to me, that's really, really, really cool. But that's not really what you know, I want you to understand. So today, I will just share with you like a way by which we can understand how to deal with recursion using a circular environment. Okay, so far? All right. So let's move forward. Okay, so let me give you this idea of a circular environment or a circular scope. For the class lecture only, I'm going to give you the dirty solution, but I hate to teach something that's dirty, right? So I don't want to teach you the dirty solution. So I'm going to try and teach you the nice solution, the solution that uses object-oriented programming and Scala and functional programming and all those nice things to come up with something more elegant, right? But I will show you the dirty solution because the dirty solution really gives you the motivation for the clean solution. But I did not bother writing up the dirty solution. So this is important that you follow along, but this part is not in the notes. Okay, so how do we go about it? So let us do this. So let us take this program, let rec fact equals function of x. Okay, and now here you fill in the body of the factorial function. And one thing I hope you get from the PL class is you are able to write the factorial function no matter what time of the night you're woken up and someone asks you to write the factorial function. Let's say you're sleeping and your friend wakes you up and says, I need the factorial function now, the world's coming to an end. Well, first things, you have to defriend them. But second thing, you need to be able to write the factorial function. All right. So this body of the factorial function, imagine cut and paste it from what I wrote at the beginning of this lecture. Okay. With that being said, let us say you have this program and you are going to execute this program. Wow, write a factorial function to prove that you're not a robot. Well, it's actually the other way around. I mean, if you wrote the factorial function perfectly, you may prove that you are a robot. Anyway, that's a discussion I'm not willing to have right now. But let's figure out like how do we handle this? Imagine you are the interpreter. Okay. Now, what happened if this rec was not there? So for the time being, forget that this rec was there. What happened in the last lecture? If this rec was not there, when the interpreter encounters this definition, it's going to make it into a closure. And it's going to make it into a closure of X with this body and the environment at the time you encountered the factorial function. Let's call that the environment, env. Is that okay? Okay, we would have done that. And then we would have taken care of this let binding. And so the new environment, so the old environment used to be env. And so the new environment is env extended with factorial being a closure of X body and the old env. So this is the old env. Let me maybe as well, I might as well call this the old env. So this is the old env. Is that okay so far? Are you with me so far? This is important, right? And this is old env. Okay. Now with this environment, last lecture, we would have gone on to execute factorial of 10. Okay. When we executed factorial of 10, we would have then chosen to execute the body. So we would have chosen to execute the body, evaluate the body under the old environment with X mapping to 10. Are you with me so far? Should I repeat this argument, because this is the crux of today's lecture. If you get this, the rest of the lecture is just smooth. Okay. If you're with me so far, then answer the key question. What goes wrong now? Remember, we don't have the let rect. We just have the let from the last time. Can you tell me what goes wrong in terms of the things that I've written on my screen? Out of scope, right? Okay, so specifically, what does it mean? So Kevin got it, right? So it means that because remember, so Kevin and John got it. Angel, you're right. It is out of scope, but I need more of the inner workings or the mechanics of how the eval works. But you're right as well. Okay, so remember the body has a reference to fact. So in somewhere there's a ident of fact sub-expression in the body. Okay, so it is going to call fact. But this environment, old environment extended with X equals 10, does not have fact in it. Okay, and that was how we manage scope for let bindings. Okay, so what are we going to do? How are we going to fix it? So the fix is very simple. So I'm going to get rid of all of this because this is all old stuff, right? So how are we going to fix it today? So today, remember, we have let rec. So we have let rec today. So what should we do here? When you see a let rec, what we are going to do is we are going to introduce a circular environment. So what does it mean? So we are no longer going to handle it like this. When you see a let rec, what you're going to do is you're still going to create a closure. So you're still going to say, here is my old environment. Here is fact. I'm still going to associate fact with the closure, okay, of X, of body. And then remember, there needs to be an environment here. Okay, what environment should I have here? Obviously, in the previous solution, I had the old environment, and that doesn't work, right? So in today's solution, and here is like, if you have some music, like, where, you're talking about the arrival of the solution, this is the answer. The environment is basically this whole thing back. This is kind of a little bit mind-boggling. Remember, there needs to be an environment here, right? What you do is you make a circular definition back to the old environment. So you say, this environment, remember, a closure needs to have a parameter, it needs to have a body, and it needs to have an environment, right? So this environment is going to be the environment with the fact bound to closure X body environment. So if I create this kind of a circularity, I claim that everything works out. Okay, I'm just silent because this needs to sink in for a second. But this is basically the crux of today's solution. We are going to introduce this circularity back. And once we introduce this circularity back, everything just works out. How do we do this? Okay, so today, let's make sure that it does work out. So shall we see that this works out? So suppose I handle the recursive definition like this. And now I go on to process fact of 10. Okay, so what is fact? So what is fact? So I look up fact from my environment. So let's call this env. I look up fact from environment. So if I look up fact, fact comes out to be closure of x, body, and env. What is env? Env is this red environment. Okay, so Sebastian asked the $1,000,000 question, right? How do you reference that environment? We'll figure that out, okay? But let us say that we somehow managed to pull this off, right? In C++, let's say this was a pointer to an environment, and you basically had a circular pointer, right? C++ allows you to do all kinds of things. You could easily do this in your data structures class. And I bet you have done this in your data structures class, right? Like you can have a pointer from inside a structure back to the root of the structure or something, right? You can always do this in a suitable language. You can always do this, right? In fact, I think you can do this in Scala as well. I'll show you. I mean, it's a little bit how to put it. Yeah, it's going to be a little harder to do it in Scala directly, but I'll show you how to do it, right? That's the topic for today. But is this okay? So when I start with factorial of 10, factorial resolves to this closure. 10 is the number 10. So now I go ahead and I say, evaluate the body under environment extended by mapping x to 10. But how does that look? Pictorially, that looks like this. So now you have old environment below. You have fact, which is going to be a closure of x, body, and environment, but that environment is circularly pointing to here. And then you extend it with x equals 10, so you stack x 10 on top. And now you execute the body of the function under this environment, under this crazy environment. And this pointer, env, is to this part, the part that excludes x. So it's to this part, the part that excludes x. So you're tacking x equals 10 on top of whatever was there. Is that okay? Now, given that the body itself is, what is body? So remember, body itself is if x less than equal to 1, then 1, else fact x minus 1 times x. So, and this under this environment, so under the environment that I put a blue box around, can this body be executed? Can you execute this body under this new environment? Okay, so all right. So before I ask the question, let me answer Sebastian's question. So Sebastian asks, how does it map fact to a closure? So the point here is, what is fact? Fact is a function, right? And in our language, the value type for functions is a closure. So I'm not going to change it. So previous lecture, we saw that functions have a value type, which was closure. And this was for non-recursive functions. And today, we are still going to do for recursive functions the same thing. They are also going to be represented by a closure, but I'm going to make a trick with the environment. The environment in the closure is going to have a circular reference back. Okay, but functions are still going to be closure so that everything I used in the previous lecture will just work seamlessly. Is this okay? Okay, now do you see that if I made a call to fact of 10, do you see that I have everything I need to evaluate the body of the function? Because, okay, could I explain why x maps to 10 stacks on top? Very good, this is a good question. So this is my convention, right? So remember, in environment, I keep my old environment. So I mentioned like 3 or 4 lectures ago that you can imagine environments as stacks, right? Where the latest binding that you are bringing up will be at the top of your stack or top of your list, and every other binding will be at, below it, right? So in that sense, if you have your old environment and you say old environment extend, let's say x is 10, then you would have old environment all the way below, and then you'll have x is 10 here. Okay, so this is just the way I'm representing things today. Okay, but we saw this 2 or 3 lectures ago when we were looking at scopes and scope chains, and this is where we are going to use it. The fact that environments don't have to be a Scala map. And in fact, you cannot do this with a Scala map. What you would do is you would make an environment something like a list or a linked list or a stack, okay, or more of what we call a linear structure or a straight line structure, okay. And with that, we have this x maps to 10 is on top of the previous thing. Is that okay? All right. Very good. Very good. So this is crucial, right? So this lecture is very intricate, but given all of this, given this funny looking environment with the circularity in it, can the body of this function be executed now? Do I know what x is? I know what x is. I know what fact is, right? So I can execute it. And then if I make a call, if I make a recursive call to fact of 9, how does that call get handled? Well, that call gets handled like this. So what is fact? Remember, fact itself is a closure. So if I look up fact, I get its closure of x, of body, and some funny environment. But what is that funny environment? That's just a reference back to this guy, fact and old, whatever the old stuff, old environment stuff was below it. So when I look up fact of 9, fact becomes this. And then the rule for executing a function is you take the environment in the closure, and then to that you map x maps to 9. Okay, we'll visualize this. Thankfully, the Lettuce Playground tool that I have also handles recursive functions. So I'm going to help you visualize this in a second. But is this okay? So you are now able to execute the recursion simply because when you see a let rec, you have artificially forced this circularity, right? You have artificially said the recursive function maps to a closure with the formal parameter, with the body, and the environment is this environment, where the environment is the environment with fact mapping to the recursive closure. So this picture here is super important. Is that okay? So then the question is, how do we do this picture, right? How do we implement this picture? And like I said, in a language like C or C++, this is a piece of cake. You can use pointers and so on, and you can implement this quite easily. Okay, so question from Evan. Fact is contained within its own environment. Even better, what is happening is fact is a closure. So fact is a closure. Okay, fact is a closure whose environment, so remember the captured environment in the closure contains in itself fact, which is basically going to be this guy. Okay, so in other words, the environment in the closure, knows fact. Which means, what does it know about fact? That it's this closure. Is that okay? And that's just me unwinding this diagram. So fact is a closure, and inside the closure, you know about fact. Well, that is a closure. Inside the closure, you know about fact. So I keep a circular reference back to myself. Does that make sense? So you can say fact is contained within its own environment, or fact contains in itself the environment that contains itself, right? So we just make a circularity. Then you're saying the chicken came from the egg, and I'm saying the egg came from the chicken. Is that good? Because this is super important. And in C++, this is a piece of cake to implement, but Scala does not have pointers, right? How do I pull this off in Scala? And that's the second question I'm going to address right now. So if this is clear that we need some kind of circular environment, I'm going to talk about how am I going to pull this off in Scala. Okay, Sahil has an excellent observation that each recursive step will only have the X value from the last step in the environment. Absolutely. So maybe let's do it like this. I'm going to go to the lattice playground and walk you through how this works, right? By showing you factorial and imagining circular scopes. Okay, so here we are back to, hopefully you can see the lattice playground thing. Okay, let me click on factorial. Okay, so this is the factorial function, let rec. I did not allow a space between let and rec in my grammar. I have to fix it. But it's let rec fact equals function of x. If x is less than equal to 1, then 1, else fact of x minus 1 times x in fact of 10. Is this okay? Okay. Now I'm going to execute this in an empty environment. Okay. So I start, and you can see here, I just wrote fact is a recursive function of x. I did not write that circular arrow back, but you have to imagine that there is a circular arrow back because my graphic skills only go so far. Okay, I didn't have the skill to draw that circular arrow back. I guess if desperate, I could have done that, but you have to imagine this is that closure of x, blah, 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 with that circular arrow back. I'm just calling it recursive function. Is that okay? So imagine that circular arrow back. Okay, so now I'm calling fact of 10. So if you go back, you see fact is a closure of x with blah, blah, blah. Okay, and then 10 is just 10. So now I am in fact, and now you see x is 10 is on top. X is 10 is on top of my environment. Fact still maps to that circular closure. I'm just calling it recursive function, but there is a circular reference back. Okay, and finally you have all of this. Okay, and then we keep going. So here you execute the if then else, and then you fall into the else branch. So when you fall into the else branch, fact is still a closure because you still know that fact lies in your environment, right? Because of the circularity. Okay, x minus 1 is 9. And now you are back onto the same body of the fact function in like a recursive step. Now x is 9 and fact is still the circular environment. So the value of x is going to be on the top of the environment, right, at every single time. Okay, now x is 8. You can see I'm just clicking on. X is 7. I should have like a multiple step button here, which I can add. X is 6. Okay, so you keep going. It takes a long time, too many clicks here, but I'm just going to click as fast as I can. X is 4. X is 3. But you can see how the fact always remains as a circular closure. I'm not going to get rid of that. X is 2. Finally, you get x is 1. You get to the base case. And now you're going back on your recursive chain. So this is not tail recursive. It's working on the Scala stack. Now it's rewinding itself. You can see now your x is 7, your x is 8, right? X is 9, x is 10. You're rewinding back. I didn't show you all that result, and then you get back. Okay. So this is mildly instructive, right? So it tells you how this circular scope idea is going to work. If you can pull it off, it actually works. It solves the recursive problem. Now the question is, how do we make it work? Is that okay? All right. So now comes the idea, the key idea of how we are going to make this work. Okay. So Angel asked this question, are we going to write it as a tail recursive later on? Yes, we are. It's going to be a little harder. Okay, so here's what I'm going to do. In 2 weeks, I'm going to show you a generic method to write every recursive function as a tail recursive function. Okay, I'll show you how that's done. Okay, so to answer Angel's question, once I show you how that's done, there is a way by which you can take the entire interpreter that we have written so far and make that entire interpreter tail recursive. Okay, so that is number one. Number two is tail call elimination is more of a compiler thing, right? So what you really want to do in a compiler is when you have a tail call, you would change it from a call instruction in your processor to a go to instruction. Okay, and that's what tail call elimination does. It's more of a compiler thing. Interpreters don't generally do tail call elimination because that's not the job of an interpreter. Is the difference clear? Like when you're doing your project one, you're writing a compiler. In project one, we did not handle function calls, but if we had handled function calls, I could have shown you like how tail call elimination works, because then you'd have changed a call instruction in your program to a go to instruction. So instead of calling, you'd have gone to the location in the program and directly executed that. Right now, I'm not going to do that. Okay, so we will write it as a tail recursive function later. So Evan's question is, are these previous environments stored on some sort of stack that's not pictured? Exactly. They are stored actually not on some sort of stack. They are stored on the Scala stack. Remember, you have your eval function running in Scala. Scala has a stack to run function calls. That stack is storing the environments. Is that okay? All right, I hope so. Yes, very good. So now let me show you how to take care of the circularity. All right. So the way I take care of the circularity is I am not going to put a circular pointer. This is not good, not good for many, many, many reasons. Okay. Even if I manage to make a circular pointer, this is not good. And one of the main reasons you don't want circular pointers in your program ever is in a garbage collected language. We'll study a little bit more about garbage collection. But what is garbage collection? Remember, Scala does not have a delete instruction. Scala has new, but Scala does not have a delete like C++. So what is it doing? Is it's doing memory management for you. So when it figures out that you are no longer needing to use a bit of memory you allocated, Scala will garbage collect it for you. So you don't have to understand, okay, here I have used the new operator to allocate memory. I have to deallocate it myself. That's C++ mentality. In Scala, you don't do that. You essentially use garbage collection. So the runtime or JVM does garbage collection for you. And when you create these kinds of circular references back, there is a kind of garbage collector called reference counting garbage collector that's never going to be able to free this data structure. Okay, so this will just remain as a memory leak that will never be collected. Okay, so this is not a very good thing to do, not a good thing to do. Okay, and circular linked lists are very dangerous data structures. I'm sure in data structures, at least some of you must have gotten somehow a circularity in your linked list implementation, and you would immediately find out, oh no, I created a circular linked list and now I have an infinite loop, right? How would I make my students in data structures create a circular linked list? I would ask them to implement an append function of two lists, L1 and L2, right? Two linked lists. And I would pass the same list L and L to the append function. And so what people would do is they would take the first list L and they would take the same L. They would take the tail of the first list and make it the head of the second list, right? So ideally, that's what you want to do. But if these are the same lists, what you end up doing is not this. You would end up doing this. So you would have created a circular linked list. It's kind of so easy to lose sight that if you do append on linked list and both the lists are the same list, then you have to handle it by making a copy of the second list if both the lists are the same, making a new copy and then do the append. Otherwise, you're going to have a circularity. And then if you're looking for something in the list, you're going to go into an infinite loop. Okay. These are all 2270 nightmares. Okay. 2270, the course that you took. before you had to take this class, right? So let's not do that. Let's not do circularities. Then what do we do? So this is the idea. So I'm going to talk about how to do it without introducing a circularity. All right. So the way we do it is by creating a data type for environments. So what does it mean? From the outside, I'm going to give you some functions that you're going to be able to call and work with to manipulate environment. So what are the functions I'm going to provide you? I'm going to provide you a function to create an empty environment. I'm going to create a function to extend an environment. So if you have an environment and you want to extend it with a new binding, I will create a function for that. I will create a function to allow you to look up an environment. So this is extend has two arguments, a string and a value and old environment. Okay, so then this returns a new environment. Okay, so I'm going to create a function for extending. I'm going to create a function for lookup. So in lookup, I'll give you a string and I'll give you an environment, and you have to return a Boolean, which is going to be true if the string, or not a Boolean, return a value. So if the string exists in the environment, then you return the value. If the string does not exist in the environment, return error. Okay, I think we saw this, right? We saw some of this a few lectures ago. Today, I'm going to add a new kind of extension, which is going to be called the recursive extension. So I'm going to ask you to recursively extend an environment, okay, where I'm going to have a string, which is the name of the function. I'm going to have, Okay, I'm going to have a string, which is the name of the function. I'm going to have a string, which is the formal parameter. I'm going to have the string, which is the name of the function, string, which is the formal parameter. I'm going to give you the body of the function, which is an expression. And I'm going to give you the old environment. Okay. Now this extend rec needs to create something like this. So it will create this picture. So you have your old environment. You have the name of the function will map to a closure of the formal parameter, the body, and a reference back to itself. Okay, so I need to create this illusion whenever I call extend rec of a string, a formal parameter, a body, and an old environment. Is that okay? So I need to create this illusion. So how do I do it? Okay, so I'm going to give you the solution. All right, I'm going to give you the solution, and then we'll talk about how this solution is going to solve everything we need. And then I'll talk about the idea behind the solution. Is that okay? So let's look at the solution directly in Scala. So I'm going to go back to Scala, and I'm going to go back to my notebook, and I'm going to show you how the solution works. All right. So what I'm going to do is I'm going to create my environment as a trait. So I'm going to call it sealed trait environment. Okay. It's no longer going to be a map. It's going to be a inductive data type defined by a grammar. I'm not going to write the grammar. I'm just going to directly give you the Scala definition. Okay. So I'm going to declare a sealed trait environment. And now I'm going to say case object empty environment extends environment. So what is this empty environment? This is going to represent an environment with nothing in it. Is that okay? So this is going to represent an environment with nothing in it, and that's called the empty environment. And I'm going to make it a case object. Is that okay? It's like the nil. Good so far? Next, I'm going to define a case class called extend. This is the normal non-recursive extend, which has a string, which has a value, and which has an old environment called sigma. So this is saying, take the old environment sigma and now bind x with the value v. If x did not exist in the old environment, then in the environment that you create by extending in the result, then x will map to v. If x already mapped to something in the old environment, then forget that mapping. In the new environment, x maps to v. Is this okay? Empty environment and extend environment, okay so far? Now let's get to the environment that we care about. And this is called the extend recursive environment. In the extend recursive environment, I keep the name of a function as a string. I keep a formal parameter as a string. I keep the body of the function as a string. And I keep the old environment as an environment. Okay. And this is supposed to help me. This is supposed to help me extend rec helps me create the illusion of a circular scope. Okay. So how am I going to create the illusion of a circular scope? Is that okay? So now I'm going to show you how to create the illusion of a circular scope. So what does a circular scope need to do? So let me give you an example. Okay, so let me go back to my drawing board, and let me motivate this by asking you some questions. Okay, so let me create like an environment with a circularity, and let me ask you the following. Okay, so let's do this. Let's create an example. Let's create an example, and hopefully this concept is clear with the example. Okay, so here's what I'm going to do. So I'm going to say, I'm going to have an environment where x maps to 5. On top of that, I have y maps to 10. And on top of that, I have fact maps to closure of x, some body expression, and this everything from here below. Okay, so when I refer to this, it means everything from fact, y, and x. Okay, so that environment. And then let's say z maps to 15. Okay, and let's say w maps to, or x maps to 45. So let's take this as an environment. Okay, now the internals, like put it inside a box, and let's not look at the internals. Okay, but let me ask some queries of this environment. Suppose I said look up z in this environment. Let's call this E and B 0, 0 for the base environment. What happens if I call lookup z E and B 0? What is the value that I should return? Anyone? So what value should I return if I say lookup z in this environment? 15. Is that okay? 15. What value should I return if I say lookup x in this environment? 45. You will never return 5 because the 45 will override the earlier 5. Okay, 45. What value should you return if I say lookup closure? Sorry, not closure. What am I talking about? Lookup fact in this environment. Okay, is exactly what closure will I return? So I'll return a closure of x of body expression, and I would return an environment, but that environment will have what in it? It will be everything from here onwards. Everything from here onwards. Is that okay? that circular reference back and all that. Is that okay? So what am I going to do is I am going to not represent. So as long as I can implement some lookup function and all that, as long as I can implement this functionality, the internal representation of how I represent it does not matter. So I'm not going to represent this environment like this. Instead, I'm going to represent this environment like this. I'm going to say extend of x of 45, comma, extend of z of 15, comma, extend rec, and here comes the kicker, of fact of x of body, comma, extend y 10, comma, extend x 5, comma, empty. So I'm going to create this big environment in my grammar. Okay. All right. So yes. So Logan says lookup X in the environment that you get from lookup fact will be fine. Yes. Almost lookup fact. Remember lookup fact. So Logan has a question whether lookup of X of lookup of fact is 5. So let me address Logan's question. Remember, when I look up fact, I get a closure, which is a expression, which is going to be a formal parameter, an expression, and an environment. And if I look up X in this environment inside the closure, then I get 5. Okay, not literally like looking up in the So literally what you wrote would not work. But if you dig into the closure and you fish the environment out and look up X, then you will get 5. You're right. Okay. So going back to my thread line of thought, instead of representing my environment using this linked list, circular linked list mess, I'm going to represent my environment using this case classes, right? Using a trait and a case class, something almost akin to an abstract syntax tree, but for environment. So I'm going to use this abstract syntax tree. And look, there is no circular references here. There is no circular references in the way I represent the environment. Is that okay? So if you go back to my code, let me now show you how I'm going to represent this whole thing, right? How is this whole thing working now? So to understand how this whole thing works, let us go back and look into how lookup is implemented now. Okay, so this is the function for lookup. So I'm looking up from an environment whether there exists a string. Okay, so I changed the order. The string should have come first, the environment next. I'm implementing it with the environment first and the string next. I hope that's okay. I match the environment and I say, if my environment is empty and I try to look up a string, that can't happen. So the string cannot be found in the environment. So I throw an illegal argument exception, but technically I should have returned error. Okay, but since I'm not handling error the proper way, I throw an exception. But technically, according to my definition, this should have been an error. Okay. Now let's look at the case for extend, right? Now I'm saying for extend, if my environment is of the form extend y with value v, and I don't care what comes afterwards, if y is the same as what I'm looking for, so this x is what I'm looking for, and this y is in the environment. So here I hit a match. I hit a match for x. So return b. Is that okay? So this case will return b. Is that okay? Oh, hold on. Better now? Okay. Yeah, it might be a temporary glitch. Yeah. Okay. So in this case where I'm extending y with a value v, and this is the rest of the environment, or this is the old environment. right? If Y is what I'm looking for, I don't even care about what remains. I just return B. So I don't care that this is an old environment. I just say underscore. Now, if I fall through these two cases, then I get to this case. And so I need to look up the rest of the environment pi for X. Okay. So I could have written it like this. So if I could have written this code in a simpler way, I could have written it like this. If I didn't want to be fancy, I could have written this code like this. When I meet an extend case, I say if Y equals X, then V, else look up what? Look up from the rest of the environment whether X exists there. So this is just a nicer way of writing it. I was just using Scala's case pattern matching to make this look fancy. Now we come to the place where the circularity happens. So the illusion of circularity is provided here. What happens here? So suppose I come to an extend rec with the function f, the formal parameter y. So let me call this parameter. Let me call this function name. This is my function body. And this is the rest. Okay. If the x that I'm looking for is the same as the function name, if the function name is exactly what I'm looking for, then I return a closure, okay, with the formal parameter, with the body of the function. And here is where I create the circular reference. I create a reference back to sigma, this environment. I create a reference back to it, and I return this closure. Otherwise, if the function is not what I'm looking for, then fine. I will simply look up on the rest of the environment whether X exists. This is it. So this way, I do not create a circular reference up front. I create the circular reference when you ask me for it. So when you ask me for what is fact, I will create a closure. Okay, so this closure is not kept up front. This closure is being created on the fly. So when you ask for me, hey, what is fact in this environment? You would say, hey, fact is a closure with the name of the parameter for the function, with the body expression for that function. And then the environment itself is this environment. So this environment. So if you call this guy sigma, if you call this highlighted thing sigma, okay, so sigma match. So if this whole thing is sigma, then that sigma is put in here. Is that okay? So if this whole thing is sigma, okay, so if let's call this sigma, okay, so if this whole thing is sigma, then I put that sigma in here. So this refers back all the way to that extend rec. So the circularity happens exactly where I have highlighted things. Is this okay? I mean, this is a bit much, but you know, this is the crux of everything I was going to explain in this lecture. Is this okay? Any questions so far? All right, if this is okay, let's look at how we use this to build an interpreter. All right, how do we use this to build an interpreter? So here is my eval expression. Okay, here is my eval expression. Forget about my helper function. So I am trying to evaluate an expression E under an environment called environment, but this is no longer a map. This is going to be a structure which is built from seal trait environment and these case classes. So it's going to be almost like an AST, except it's a very special AST. It's for the environment. So what do I do? So the case for constant is the same. Here is the interesting case. Look at the case for identifier. So if I have an identifier X, to find out what it is, I'm going to call my lookup env function, this famous function I just wrote. I will look up that function for x. That's all. Make sense? Okay. Now plus, minus, multiplication, greater than, equal to, if then else, you can handle them the same way as before. Let me jump to let bindings. Okay. Suppose I have a let binding. I have let x equals E1 in E2. Then I recursively evaluate E1. If this was erroneous, it would have thrown an exception and already bailed. Okay. Now I build a new environment, which is, instead of using the map, like previously we extended the map E and V by adding X arrow V1, remember? Now we are simply using our extend constructor. So we are saying extend my previous environment by mapping X to V1. Okay, so it's just growing on the previous environment. So it's just like take the previous environment as a little onion, and now you have added a new layer, onion layer, where X is now mapping to V1. Is that okay? And now you evaluate your expression E2 under ENV2. So remember, we used to use a map for all of these things, and now we are not using a map anymore. We are using these funny AST-like things for environments. Is that okay? All right. How about function definition? Handled exactly the same way before. When you see a function definition, it just becomes a closure, which is the value for functions in the language. This makes environment lookup run in linear time. It does, right? It certainly does make it run in linear time. You can think of ways of like combining your map data structure with this kind of extension data structure somehow, right? To make it more efficient. But right now, yes, it makes it run in linear time. Whereas with a map, if you implemented the map carefully using a self-balanced binary tree or something, you might have pulled off like a logarithmic time. Is that okay? But yes, okay. Now let's look at function calls, right? It's the same idea. So function calls, you have the E1 and E2, so you evaluate E1 and E2. Your V1 better be a closure. You extend the environment that you're captured in your closure by mapping X to V2. It's exactly the same thing we did in the previous lecture, nothing new here. Now comes the last part, which I've been leading up to, recursion. So when I get to recursion, I create this special environment, which is going to be a circular environment. So if I am defining a recursive function with formal parameter x with the body of the function fexpr, so then I say make a recursive extension to my old environment by having recursive function x and fexpr as ingredients. And then evaluate the rest of the recursive function, which is the part after the in, the BEXPR, inside this newly created environment called ENV2. That is it. This handles recursion. And what is the main trick here? The trick here is I am not creating a circular reference up front. Instead, I am storing all the ingredients that are needed for a circular reference. I am storing all the ingredients that are needed to create a circular scope. But I never store that circular scope in memory. And when you look up, so when you ask me for it, when you ask me for that function in the special extend rec, I will then and only then create this closure for you with the parameter, with the body of the function, and the reference back to the environment sigma. So I will create it, but only when you ask for it. I am not going to store it. So if you wanted to draw a picture, the way this will work is like this. If you wanted to draw a picture, the way this works then is like this. Okay, so the way this works is like this. So let me roughly give you an idea of like how did we make this work. So the way we would have made this work then is, suppose you have your factorial function and you have your rest of the stuff. I would have said factorial is something like a extend rec. And I would have remembered that it's called factorial. I would have remembered that it has a formal parameter x. I would have remembered there is a body of the function. So I would have remembered all of this. And here is the old environment. Okay, so I would have remembered that this is the old environment and all that. So I keep all the ingredients, Now, if I am asked to look up fact, okay, and by the way, there is no circularity here. There is no circularity here. But if I am asked to look up fact, then what I do is I create, and now I create a closure. Now I create a closure. I copy this X here. I copy this body here. And I copy this environment here. And I return this closure. But remember, this closure is created afresh every time I ask for fact. So if you ask for fact again, I will create again a closure. I will call X, I will call body, and I will create a reference to M. So this reference is a reference here. This reference is a reference here. But what is not happening is there is no reference from anywhere here to this closure. No such reference exists. So there is no circularity. You see that? Only the ingredients exist. Every time you ask for it, I create a closure. I put the environment, I put the X, I put the body, and then I put the environment. But that does not create a circularity. Because from this extend rec business, there is no link, direct link to the closure in the memory. Is this okay? Okay, so I mean, there's good news and there's bad news. The good news is this is just about the trickiest thing that I could have taught you in this class, right? So that's the good news. Uh, the bad news is you have to understand this, right? So this is kind of like you have to understand this. Okay, yes, so Logan has it exactly right. So once the references keep running, it will run into the empty environment and stop, right? Because you do have this chain, right? So once you keep going, so you get to fact, and then you'll go into rest and rest and rest, and you'll get to the empty environment, right? So I do keep a structure where you do keep a straight line linked list, but if needed, you create this reference, this closure, but there is no circularity. Okay, so the thing that I would need from you is to understand this to an extent, because I don't think you will ever, I mean, very few of you will ever implement recursion in a real language like this. Having said that, I think the ideas matter a lot. The fact that there are these tricks, and the fact that you can create these circular references on demand, and you can do these kinds of data structuring tricks, I think is important. And I think you may end up in situations where you may have to create these kinds of intricate ways to, in a different situation, you may want to create this kind of use this trick. Okay, so this is just something like, advanced programming, something to understand how we are getting around this problem. Okay, and the important fact is to understand that you can use a data type, or what's called an abstract data type, and you can implement the lookup function without worrying about what the internals look like. All right. Um, so this has been like a rather, I know, long and tiring lecture, but this is more or less what I wanted to say, and I will stop right there. Thank you very much. You should read the notes. You may want to skip the Y Combinator part and read the rest of the notes, uh, and hopefully it will make sense to you. Okay, so I'll see you next lecture. Thank you, and I will stay back for, I have like 15 minutes. I can stay back until 7, so that I can, if there are any questions, I can answer. All right, thanks.